Okay, so in this problem, we're told a police car sounding a siren with a frequency of 1,280 hertz is traveling at 120 kilometers per hour. A, what frequencies does an observer standing next to the road hear as the car approaches and as it recedes? B, what frequencies are heard in a car traveling 90 kilometers per hour in the opposite direction before and after passing the police car? And C, the police car passes a car traveling in the same direction at 80 kilometers per hour. What two frequencies are heard in this car? So in this problem, we have a bunch of scenarios going on. So I went ahead and broke them down, A, B, and C down here. And so we're just going to focus on one at a time. So let's just go ahead and start with A. So for A, we have this police car, right, in two scenarios. So we have basically when it's approaching and when it's receding. So we have approaching is when it's going towards our person. Receding means when it's going away. So we know we have a police car traveling 120 kilometers per hour. And we know it has a frequency of 1,280 hertz. And so in one scenario, we're going to be finding the frequency that the observer is going to hear. And then in the second one, we're going to find the frequency when it's going away. So basically, the frequency the observer is going to hear when it approaches and when it leaves. So in order to do this, the first thing that we're going to do is convert this into meters per second, just because you'll see in a second, it makes it a lot easier to solve. So let's start with that. So 120 kilometers per hour. We know that there is 1 kilometer for every 1,000 meters. So these will cancel just like that. Now we have it in meters. To get rid of the hour, there's 1 hour for every 60 minutes. And then we also know 1 minute is 60 seconds. So your hours will cancel there, minutes will cancel, and then boom. So 120 times 1,000 divided by 60 divided by 60 again. So when you do this, you'll have meters per second, and you'll get 33.33, and the units are going to be meters per second, which is what I said before. So now we have the velocity of our police car in meters per second. So what we can do is actually talk about how we're going to solve for this. So these problems are pretty simple. You're just going to use some of the Doppler effect formulas. And so the formula we're going to use for this one is this formula right here. So f prime is basically going to be the frequency that the person is going to hear, right? So the prime just means that this person's hearing it. So in this case, it's going to be equal to f, which is the frequency of the object, right? That is like that they're hearing. So in this case, it's the police car. It's normal one, right? It's actual frequency. And then you divide that by 1 minus the speed of, or the velocity of your object. In this case, it's the car, so we'll say VP for the police car, divided by the velocity of sound. And then you go ahead and, yeah, that's your formula. So if we know the frequency of the object that's moving and we know its velocity, we can figure out the frequency interpreted by an object that's not moving at all. So this formula only works if the object, the one that's hearing it, isn't moving. So as long as the observer's not moving, you use this formula for an object that is moving. And so the difference is here, we're going to call f prime just for the B part. So you can say this one's for it moving toward, and this one's for receding. The difference here is just the sign at the bottom. So for this one, it's going to be plus instead of minus like the last one. Now, why is that? So the reason that is because you should know if an object traveling towards you, you're going to hear a greater frequency than what it actually is. And the minus sign, notice that this value on the bottom will become smaller because we have that minus sign there, which makes this frequency that it's going to interpret greater. Because if the denominator is smaller than 1, the value increases. Now for this one, if the denominator gets bigger, the value will decrease, right? Because if you divide by something bigger or greater than 1, your value decreases. So when it goes away, you actually experience you hear a lower frequency. So hopefully that makes sense. Let's go ahead and plug these in. So f prime is equal to the frequency, which we know is 1,280 hertz. Dividing that by 1 minus the velocity of the police car is what we just found up here, 33 meters per second. That's supposed to be a 3. And then the velocity of sound, I didn't mention that, but it's just a constant value. So we're assuming that this is at 20 degrees Celsius. And so the sound travels at 343 meters per second. So 343. And yeah, so let's plug this in. So 33.33 divided by 343, 1 minus that value, and then divide 1280 by that. So you're going to get 1417.76. So I'll just say 1418 hertz. So that's your answer for the first part. So when they say, what frequencies does it observe as the car approaches? So this one is the approaching. Keep that in mind. Approaching. So that's the frequency that they'll hear when it's approaching. And then receding, we have F, which is, what was it again? 1280? Yeah. 1280 over 1 plus the velocity of our police car, which was 33, yeah, 33.33, divided by the velocity of the sound, 343. And let's see what this is. So we got 33.33 divided by 343, 1 minus that value, and then 1280 divided by that value. So, I did minus, my bad, it's plus. So 33.33 divided by 343 plus 1, 1280 divided by that value. You'll get 1166.64. So we're going to say 1167 hertz. Keep in mind this is for receding. And yeah, so these are going to be your answers for A. When it's approaching, 1418. And then when it's receding, 1167 hertz. So those are your answers to A. Let's move on to B now. So for B, what do we have in B? So let me read it again. What frequencies are heard in a car traveling at 90 kilometers per hour in the opposite direction before and after passing the police car? So for this one, we have them going in the opposite direction. So instead of a person, we have a car now, and we're going to find when they're approaching each other, like both going in together, and then we're also going to find it when it goes out. So we're trying to find the frequency that the heard in the car. So what the car is going to hear from this police car when it's going towards the police car, and basically when it's going away. But keep in mind the difference in this problem is they're actually both moving in this case, versus the last one, you only had the police car actually moving. So that's the difference in this problem. It's not going to change that much, except for we just use a different formula. So the first thing I'm going to do is convert 90 kilometers per hour into meters per second, just like we did up there, because it's much easier to work with. So you should just know how to do this again, right? Just replace this number. Oh, shoot. Oh, okay. Just replace this number with 90, and we'll figure out what we get, because it's just the same thing. So 90 times 1,000 divided by 60 divided by 60. So 25. Yeah, 25 meters per second. I'll write that. So we'll call it VC for the velocity of the car. 25 meters per second. Okay. So now that we know that, let's talk about the formula we're going to use. So we can call it F prime again for the frequency that the car is going to interpret. We'll call it FC prime, I guess. So what it's going to be equal to is F divided by the velocity of the sound plus the velocity of the observer divided by the velocity of the sound minus the velocity of your car, right? So the police car, so we'll just call it VP for the police car again. So notice the way this works is we have the velocity of the sound plus the velocity of the observer. So you always have this on top. The reason why this is a plus is because we're going towards it, okay? Which should make sense, because if we're going towards it, the value should increase. And if our denominator is adding, or our numerator is adding, the value is going to increase. Versus the bottom, it's going towards it too. So it's also going towards it. So I know my value should increase as a result of that, this value here. So if I want it to increase, the denominator has to decrease, which is why we have a minus sign there. And yeah, so for this one, if you can try and guess which one it's going to be, well, we're going away now, so on the top, it's actually going to be minus, right? Because we know it's decreasing. And if we also want it to decrease, since this one's going away, you have plus on the bottom, right? Because a plus on the bottom will make this value smaller. So hopefully that makes sense. And yeah, so you're just going to use these two formulas, just plug and chug to solve. So let's go ahead and do that. So once again, the police car's frequency is 1280. That was what it was, yeah. So 1280. The velocity of sound is 343, plus the velocity of our observer, which was our car, which we know travels 25 meters per second, divided by 343 minus 33.33, right? The velocity of our police car. I'll plug it in a second. Let me do this one. So for this one, again, 1280, the velocity of sound is 343 minus the velocity of our observer, which is the car, divided by 343 plus the velocity of our police car, which was 33.33. And yeah, so let's see what these are. 343 plus 25 divided by 343 minus 33.33 times 1280. So you'll get 1521.10. We're just going to say 1521 hertz. So keep in mind that this is when they're approaching each other. And then for this one, let's see what it is. 343 minus 25 divided by 343 plus 33.33 times 1280. For this one, you will get 1081.60. So we'll just say 1080 hertz. So keep in mind, this is when they're now going apart from each other. So keep in mind that these are for their respective scenarios. So you just have to make sure you specify that when you write that in your answer. So when your teacher sees it, he or she understands what's going on. And yeah, so these are your answers for B. Now let's move on to the last one. So for the last one, C, what we want to do is notice what's going on. So for this one, they're actually going to both be traveling in the same exact direction. Unlike the last one where they were traveling opposite directions, right, where they passed by, this one they're going to be traveling in the same direction. So notice in the beginning, we have the car traveling this way and the police car. So it's going to be approaching it this way. And then for this one, it's actually going to be going past it this time. So before it's approaching it, and then after it's going away from it. But yeah, so, and this is all relative to the car. So just like the last two problems, we have to find the car in terms of meters per second, its velocity. So let's do that. So once again, just plug in 80 up here instead of 120. Oh, sorry about that. So we just have 80. And then obviously we have to multiply by 1,000. Divide by 60. Divide by 60. So for this one, you'll get 60. Wait, did I mess that up? Oh yeah, my bad. It's not 60. It is 22.22. Sorry about that. So the velocity of the car in this one is 22.22 meters per second. Okay, cool. So we've got that now, and let's talk about how we're going to solve this. Okay, so in order to solve this one, what we're going to use is the same formula that we used for this problem, except for we're going to change a few things. So instead of it being different signs, they're actually going to be the same sign, okay? So let's go ahead and write it down. So obviously this one is also based on what it's hearing from the police car, the frequency. So it's going to be equal to F of the velocity of sound. And then we'll decide the sign in a second. I want that to be explained. So we have velocity of sound and then velocity of the police car. Let me write these for both of them, and then we'll talk about which sign we're going to have to use. There we go. Okay, cool. So starting off with the first one. So notice that the police car is going to be going towards it, okay? but the car is also going away from it. So since the car is traveling opposite the police car, this value is going to be a minus. So since it's going the opposite way of the police car, it's going to be like this. And then on the bottom, it's also going to be a minus sign. Now this is because the police car is going towards it. So we know the police car is going towards it, so it's minus, but the car is going away, so it's minus. So if they're traveling in the same direction like this, it's going to be like that. And then in this case, right, so you always start off the top based on, is the observer moving towards or away from it? Imagine it's just stationary, the police car. Since it's moving away, it's minus. And then imagine if this is stationary. Is the police car moving towards or away from it? Towards. So this is minus, so it makes the number bigger. So yeah, basically keep that in mind. So for this one, what do you think it is? So first, imagine the car by itself. Is it going towards or away from the police car? It's going towards, which means we make the top positive. Now at the bottom, is the police car going towards or away from it? It's going away from it. Therefore, the bottom also has to be plus to make this value smaller. So hopefully that makes sense. But yeah, so basically just using the same formula, you want to imagine it's frozen when you write each of these, the opposite one. Right, so for the observer, we imagine the car is frozen, it's moving away from it, therefore minus. Right, and keep in mind the signs on the bottom are opposite the direction it's moving because we want it to basically affect the actual value in the way we want it to. So that's why we make this negative if it's going towards. And yeah, so really now it's just a matter of plugging it in. So we know the frequency of the police car was 1280. Velocity of sound is 343 for both. The velocity of the police car is 33.33. The velocity of the observer is 22.22. Let me write this one out. So 1280 minus the velocity of the observer, again, 22.22. 343. Or this one's plus, sorry, I wrote minus. Plus 33.33. And yeah, so let's go ahead and see what this is. So 343 minus 22.22 divided by 343 minus 33.33 times 1280. You will get 1325.9. So we'll just say 1326 hertz. And then for this one, you will get a value of, let's just plug it in, I guess. 343 plus 2222 divided by 343 plus 33.33 times 1280. You get 1242.2. So this is going to be 1242 hertz. You can round however you'd like. I'm just rounding to the whole numbers for these. So 1326 hertz and 1242 hertz. Keep in mind these are for their respective scenarios again. So this one's when it's past, and this one when it's still approaching it. So the two frequencies are right there. But yeah, so these are going to be your answers for C. These are your answers for B, and these are your answers for A. So basically this whole problem is just about using the Doppler effect in different scenarios, whether it's approaching or going away, whether it's stationary, whether they're both moving. All these are the different types for this problem. But yeah, so those are going to go ahead and be your answers. And hopefully you found this video useful.